So this is my review of lecture 16, projection matrices and least square. And first I will discuss about some properties of the projection matrix. Professor Strang discussed about these two edge cases. So the B being perpendicular to the small p, and if B is in the subspace of A, which is also in the subspace of B because B is in the subspace of A. Let's recall that projection matrix formula is here, and recall that we have this vector B which is sticking out of our subspaces A, and we project the B so that it gives us the best estimation projection matrix P, small p here, which inside the subspaces of A. So let's start with the first one. So if the B is perpendicular to the P, then we stated that the projections of the B with if projection matrix P x on B, it will be 0. So let's continue with this one. So recall that the small p is actually just some combination, some x hat combination of the bases inside A, and we can get the x, which is the x is actually the x is let me write this down. X is the A transpose A inverse ATB. So let's write it down here. Okay, and let's see what we got here. Recall from the previous lecture that there's this kind of this orthogonal complement. So this we have a subspace A, and the orthogonal complement of subspace A is the knot space. But here we are talking about the A transpose B, so we are interested in the A transpose, which means the column space of A. So instead of the null of A, we have the null space of A transpose. So actually, if we assume that B is perpendicular to P, and we know that the null space of A transpose is perpendicular to A, and P and A sits on the same subspace, so that means this is the B. B is sitting here somewhere. I don't know how it looks like, but it's in the combination of the null space of A transpose. So this will be 0, right? Because these are orthogonal, and the dot product of this and this will be 0. So P is 0. So that's why also the matrix projections B times B will be 0. Now let me make that clear again. Where I got this is from here. Okay, and you expand the x hat, so you got like this. Okay, and then this is the capital P B, so P small b, and this is 0. Okay, so we got our proof for the first one. And the second one is, what if the B is sitting inside those subspaces of A? So we stated that it will not change. So well, geometrically speaking, it really makes sense because you already have B here sitting inside those subspaces of A. And what is the best projection? What is the best estimation of B? The B itself, of course. No matter from where flashlight, no matter how you project the B, it will be still B. So intuitively it makes sense. And now let's prove it as well, the same way as we proved this one. So we have this form right here, transpose, and then we have this A transpose A inverse A transpose B. Good. Now if B is inside those subspace of A, then how can I find the B in terms of A? Well, B will be just the same as A x hat, right? Because now B is just a combination, the x hat combination of some bases from A. So again, it's like this, just a combination of two of them. So let's substitute this into here. So I will get this form, t here, and then this will be a x hat. Okay, now see this form right here, and let's play around with the parentheses, and we will have the A transpose A inverse, and we have A transpose A. This will be equal to identity, and we will have A identity x hat, which means that the projection is the ax hat, which is equal to b. Now again, that the p is actually just the pb, and this will equal to b. So we got the second proof here. And then one more thing that I want to discuss is this identity minus p, the capital P. So recall that this figure here, so we have the subspace A, and we have the orthogonal complement of it, which is the null space of A. And here we're interested in this, so this is the row space of A, and this is the null space of A, which are orthogonal. And we have this vector B, which is sticking out. It's not inside the A, it's not inside the null space of A, so it's just there. And we're interested in finding that projection, the small p, which sits inside those subspace of A. And we, from the previous lecture, we know that there's an error vector E, which will be perpendicular to that P, and there is this projection matrix, the big P, which transform B into the small p. But what if we want to transform the B into, we want to project B into the null space of A? There must be some projection matrix there, which we can use to act on B as well, the same way as the bigger P acts on B to transpose, to project into the subspace of A. And in this case, we use the identity minus B. So Professor Shrang mentioned about this in the lecture, so I thought this is also worth mentioning. And one thing also, that this P, the E here, the vector E, is lives inside this null space of A. So we already covered the first points here, so let's move on to the second one, which is the heart of this lecture, which is the application, and we will talk about this least square also, this form. So I will just copy and paste what Professor Strang example from his lecture. So we have this measurement in terms of t with respect to the y. So we have 1, 2, 3 and 1, 2, and this is the result of our measurement 1 and y equal 2. So the goal is to find some line that kind of fit the best among those three equations. So it might be this line, it might be this line, it might be, as you can see, there are numerous possible combination of line, but let's just, for illustration purpose, let's stick with this one. And the equation of the line, the general equation is c plus dt. So c is the offset here, which can be 0 or which can be some number, and dt is the one that corresponds to the t-axis. So there are three measurements, so there are three equations. Let's create those. C plus d equal to 1, the first one here, and c equal to d equals 2, and c equals 3d equals 2. And let's turn them into a matrix form. So if I have this 1, 1 from C and 1, 2, 3 from the D element, and I want to multiply by the CD, and this is my result. And let's connect this with the previous lecture. So this one is the A subspace, and this is the solution X that we are interested in, and this is our B. But as you can see, it is not possible to find some combination out of this that resulting in B, because it doesn't exist in this subset of A. So we want to find some other combination which is belongs in P. So we no longer find B, but we find some best estimation of B. Best estimate of B, which is the P. So this is what we have been discussing so far. I assume you're already familiar with it by now. So let's do that. So we are interested in finding X now. The goal is to find X hat with what? That satisfy the baseline Y. So what is the baseline? So the condition, remember that there are a couple of possible candidates for Y. It can be like that, but here where the term least square comes in. So with minimize, also the error, which is also the ax minus b, and there's a convention of giving the square there. So this is equal to the b minus ax, of course, because this value cannot be negative. So we're interested in the length of vector e, so that's why we give it this notation and the square of them. So that's a convention. Professor Strang doesn't explain further about the reason, the actual reason why it was squared, but if you guys know, please let me know also in the comment below, and we'll move on. So we want to find this combination. We want to find the x hat, and how do we find the x hat is through this equation, which is already what we also discussed in the previous lecture. So we want to find the x hat through this equation. So we compute these A transpose A and the A transpose B. By the way, this is called also the normal equation, and Professor Strang mentioned that this is like a really most used, this is a really important equation for statistician. So whenever you want to fitting some line into some measurement, this equation always comes into play. So let's compute the A transpose A and A transpose B. So like this, and then so that we just tag B here. So when we compute them, we get the result for A transpose A and then also A transpose B. So this will result in this matrix C5 11. Nice. So we got our two lovely equation, which are 3c plus 6d and 6c plus 14d equal to 5 and 11. So I will not go rigorously into finding the c and d, but I just believe me on this one, because this is also the result on the lecture. So c and d are this number. So we find our baseline is 2 over 3 plus half t. So there you go. So this is our baseline, and this is our equation c and d. We already covered this point and this point. And another interesting thing that worth mentioning is, I think the linear algebra and the calculus way of figuring out these two equations agrees. So what I mean by that is, if I use this error function here, so the vector will equal to, the vector e is equal to, so e1 squared plus e2 squared, so each component squared, right? because I have 3 components, then I square all of them. So this will equal to like c plus d minus 1 plus c plus 2d minus 2 and c plus 3d minus 2 squared. And then how do you find, how do you minimize the e in calculus? So e is a function of c and d. So e is a function of c and d. So you find those two partial derivative of e with respect to c and with respect to d, and you set them to 0. And these two will equal to this equation here. (14d11). This is just, I think it's really beautiful to see that the two ways of computing, of getting us into these two equations lead us into the same equation. So our computation makes sense. Also, visually speaking, from this picture, I think I want to mention that E is actually this line right here, the arrow one. So the distance between our measurement and distance into P. P is here, the one that is sitting on that line. So we have P here also, P here. So this P E1, and this is a little one E2, and this is E3. And you also have P1 here, P2 here, and P3 here. And another interesting thing, that if you want to try to, geometrically, we know that the vector E itself, this E, remember from the picture, let me clear up some room here. Let's just delete this. Remember our picture of orthogonal complement. So this is subspace A, and right now the E is sits here. So this is again the row space of A, this is the null space of A. So E must be orthogonal to all the vectors sitting in the space of A. So once you got the vector E, which you can get by subtracting this the P with this Y equation, our line. Oh no, I'm sorry, which is the B times minus P1 and B2 minus B2. You get the E1, E2, E3. Let me just write that down so you can do the projection into the actual value, of course. And you can test to like verify if the E1, E2, E3 dotted by our basis of A, which is this column vector, right? Does this equal to 0? And the second basis, 1, 2, 3. How about this one? Does this equal 0? Because it will equal 0 because they are independent. So this is just another way to verify that our computation is done correctly. And now we want to go into the third point here. So if A has independent columns, then A transpose A is also invertible. So how to prove this one? So if A transpose A is invertible, then what we have known so far from the lecture is how to prove that a matrix is invertible. Let's say matrix B is invertible is by we're trying to find some solution X, which is again the null space of X, and the null space must be 0. So let's do the same thing here. So A transpose A times X equals 0, and we want to prove, we're interested in finding is X only has 0 vector as a solution. So what we do here is we can multiply both sides by the x transpose, a transpose a x, x transpose 0, and then the right hand side goes away and we're left with this. And then you can see here again by some parentheses trick, we can say that if ax equal y, then we can say that the ax transpose and ax is 0. So this is like y transpose y equals 0. And this is again some length squared of y equals 0. So some vector y with length equals 0. So that means, this means the ax must be 0. But we know that x is some matrix with some independent column. I'm sorry, I cannot spell independent correctly there. But anyway, this proves that the x must be 0. So the null space of A is 0, thus we got our proof that A with independent columns, then A transpose A is also invariable. So that's it, my review for chapter 16. Goodbye.